Hello friends, in this lecture we will discuss about the history and principles of microscopy. We will start with the history of microscopy followed by properties of light. We will then move on to the general principles of microscopy like resolution, magnification, angular aperture, numerical aperture and working distance. The microscope is one of the most valuable and useful instrument in a biology laboratory, and microscopy is the technique in which light or electrons are used to obtain magnified images of minute organisms. We will first start our discussion today with history of microscopy. Credit for the first microscope is usually given to Zacharias Janssen and his father Hans Janssen. They were Dutch spectacle makers who started experimenting with lenses around the year 1595. They put several lenses in a tube and discovered that the object near the end of the tube appeared to be greatly enlarged, more than that achieved by any simple magnifying glass by itself. Their first microscopes were more of a novelty than a scientific tool, since maximum magnification was only around 9x and the images were not very clear. Yet another pioneer in the use of microscope was Robert Hooke. He was an English philosopher and member of the Royal Society. He developed a primitive microscope as can be seen in this picture. He was the first person to observe cork under microscope and coined the term cell. He published a book called Micrographia in 1665, which among other things contained drawings of over 100 specimens and described the use and benefits of microscope. Antonie van Leeuwenhoek may not be the first person to build a microscope, but the microscopes that he made were the best ones for that time period. Also, it was he who finally put the microscope to practical and scientific uses. He was a cloth merchant but achieved greater success than his contemporaries by developing ways to make superior lenses, grinding and polishing them to get a magnification of 300x, the finest known at that time. It is said that Leeuwenhoek gained much of his inspiration from reading Hooke's Micrographia. Despite these great achievements in microscopy, microscopes didn't change much over the next 200 years. The 19th century saw dramatic progress in the development of the microscope thanks to the contributions of a few great minds. Carl Zeiss was one of them. He devoted significant efforts to the manufacture of microscopes. After almost 20 years, Zeiss had employed about 20 qualified staff members and took great pride in his prospering business. He knew that his instruments were good, but he refused to accept the trial and error method used at the time for production of the optics. So, Zeiss formed a partnership with Dr. Ernst Abbe, a brilliant physicist and mathematician. In 1872, Abbe formulated his wave theory of microscopic imaging and defined what would become known as the Abbe sign condition. The construction of microscopes with maximum resolution was possible on a sound theoretical basis and still is today. Abbe first met Otto Scott, a glass chemist, in 1881. Over the next several years, Abbe and Scott developed several new glass formulas and made adjustments to the mixing and annealing process to eliminate internal defects and produce optical grade glass with a uniform refractive index. The creation of the epochromatic objectives eliminated color aberrations, which greatly assisted bacteriologists in identifying infectious bacteria and brought the resolving power of the microscope to the limit we know today. With the microscope revolution in full swing and technology rapidly growing, scientists were able to take the foundations of microscopy and shake them up even more using new technological advances. One such scientist was an Austrian chemist, Richard Zsigmondy, who invented the ultramicroscope. This microscope worked by aiming a high-powered light beam through a colloid of particles, which allowed to see particles smaller than a wavelength of visible light. Richard Zsigmondy was awarded the Nobel Prize in Chemistry in 1925 for the discovery of the ultramicroscope. In 1932, Dutch physicist Frits Zernike discovered that he could view unstained cells using the phase angle of rays. He went on to discover the phase contrast microscope, which allowed to see colorless and transparent biological materials at a microscopic level. This brand new frontier of microscopy allowed scientists to view cells without staining them in order to view internal cell structure. The contrast enhancing technique was ideal for viewing living cells, including cultures, tissues, and microorganisms, and is still widely employed in scientific research today. In 1953, Frits Zernike won the Nobel Prize for Physics for his invention of the phase contrast microscope. But it took another 10 years to bring the first phase contrast microscope in market. Just 6 years after the invention of the phase contrast microscope came the electron microscope. As far as microscope technology goes, nothing is quite as impressive as the electron microscope. In the year 1931, physicist Ernst Ruska and German electrical engineer Max Knoll invented the electron microscope. Instead of light, the electron microscope uses a focused beam of electrons to create an image. It's capable of far greater magnification and resolution than a light microscope, making it possible to view objects as small as an atom. In 1933, they produced a transmission electron microscope with 12,000 times magnification. The picture here is that of the 1933 model of electron microscope at the Deutsches Museum. For this development, Ernst Ruska was awarded the Nobel Prize for Physics in 1986. You may wonder why only Ruska and not Knoll was awarded the Nobel Prize. Students, that is because Max Knoll died in 1969 and Nobel Prize is not given posthumously ever. Moving on now to studying the different principles of microscopy, but before that, let us study the units of measurement. We all know that microscopes are small, But how small? So small that probably thousands of them could fit on the pinpoint. Naturally, the units required to measure them also have to be small. The common units like length, sorry, the common units of length like centimeter and millimeter are also too big to measure microbes. We know that when a meter is divided into 1000 equal parts, it is a millimeter and can be expressed as 10 to the power minus 3 meter. When the millimeter is further divided into 1000 parts, each part is called a micrometer. A micrometer, formerly called micron, is equal to 10 to the power minus 6 meter. When a micrometer is further divided into 1000 parts, each part represents a nanometer. A nanometer is equal to 10 to the power minus 9 meter. Yet another unit, angstrom, is equal to 10 to the power minus 10 meter, but it is not used any longer and can be found only in old texts. It is necessary to revise the basic properties of light before we go into the details of microscopy. Light, when it travels through a medium like air or water, can have many fates. Reflection is the first property of light studied by a student of science. The bouncing back of rays of light after striking a smooth surface is called reflection. The second property is transmission. Light can pass through a glass window but not through a rock. When light passes through an object, we say that transmission has occurred. Has reflection and transmission any role to play in microscopy? Yes, it does. If we want to see the objects under a microscope, the objects should either reflect or transmit light. The third property is refraction. We know that a ray of light travels in a straight line in a given medium like air. But what happens when light passes from one medium to another? This can be understood by a simple activity. Keep a stick in a standing position in a beaker half filled with water. The stick appears bent at the water's air interface. This is because the rays of light passing through water have changed their direction when they pass from water to air. This bending of light as it passes from one material medium to another is called refraction. Thus, light rays passing from one medium to another may be either refracted or reflected. It is necessary to be familiar with and understand the principles of microscopy before taking up the different types of microscopy. These principles include wavelength of radiation, resolution, magnification, numerical aperture, and resolving power. Let us first talk about the wavelength of light. Electronic magnetic radiations include visible light, X-rays, microwaves, and radio waves. All these differ in their wavelength, that is, the length of the rays. Wavelength, represented by the Greek letter lambda, is equal to the distance between two adjacent crests or troughs of a wave, as you can see in the figure. Different colors have different wavelengths, like violet has a wavelength of 400 nanometers and red has a wavelength of 650 nanometers. The next term that you should be familiar with is resolution. Resolution is defined as the ability to distinguish two very small and closely spaced objects as separate entities. Resolution is best when the distance separating the two tiny objects is very small. If we want to see two objects as two separate things, then light has to pass through them. What would you call these two dots as? Well, they are unresolved dots. And these are resolved dots. See the difference in both the pairs of dots. If the wavelength of light is very long, the two objects will be seen as one single blurred object as in the upper figure. Therefore, shorter the wavelength, greater is the resolution. Well, so just to find out whether you have understood the concept of resolution, what do you think of this image? Yes, it is an unresolved image. What about this? It is a just resolved image. And finally, this? Well, it is a fully resolved image. Moving on now to the resolving power of a lens. It is the resolution which can be obtained by that particular lens. The smaller the distance between two objects that can be distinguished, the greater is the resolving power of the lens. If two dots are placed less than 0.25 millimeter apart, human eye cannot perceive them as two distinct dots but as a single blurred dot. This tells us that human eye has a resolving power of 0.25 millimeters. The resolving power of a lens depends upon two factors. One, wavelength of light used, and the other, power of the lens, which is determined by its numerical aperture. We will talk about the numerical aperture slightly later. Resolving power can be calculated by the formula wavelength of light upon 2 into numerical aperture, that is lambda upon twice Na. From the formula, we can understand that shorter the wavelength, greater the numerical aperture, greater is the resolving power. The commonly used lenses have a numerical aperture of 1.3. The range of wavelength of visible light is 400 nanometers to 700 nanometers. Thus, the average wavelength of visible light would be around 550 nanometers. Substituting these values in the formula, we get resolving power is equal to 550 upon 2 into 1.3, which gives us 211 nanometer or 0.21 micrometer. From these calculations, we may conclude that the smallest details that can be achieved by the light microscope are those having dimensions of around 0.2 micrometer. This is called the limit of resolution of light microscopy. Yet another important term in microscopy is angular aperture. The light from the light source emerges from the condenser in the form of an inverted cone, as can be seen in this picture. This inverted cone of light enters into the objective. The angle between the two most divergent rays that can enter the objective is defined as angular aperture of the lens. It is denoted by A. The next concept is numerical aperture. It is the light gathering ability of a microscope objective which is quantitatively expressed as a mathematical formula. It was Ernst Abbe who first described the relationship between image resolution, angular aperture and refractive index of the medium. He called the new measure of objective performance numerical aperture or NA and defined it as NA is equal to N sin theta, where theta is half of A as shown in the picture and N is the refractive index of the medium through which the rays pass. It is clear that theta can never be larger than 90 because sine of 90 is 1. So, no objective can have an NA numerically larger than the refractive index of the medium in which it is working. Thus, numerical aperture is a mathematical expression which gives the relation between the amount of light concentrated by the condenser and that collected by the objective. The most important function of a microscope is magnification. Magnification can be defined as the increase or enlargement in size of an object which is indicated by a number and x. Thus, 10x means 10 times magnified image. Most microscopes in current use are known as compound microscopes which have two lens systems. One is objective lens and available as 4x, 10x, 40x and 100x. The other lens system is ocular lens, normally available as 10x or 15x. A magnified image called the intermediate image of a specimen is produced by the objective lens. This image is further magnified by the ocular or eyepiece for viewing. This is the final magnified image. Thus, final magnification of the microscope is the product of the magnifying power of the objective lens and the magnifying power of the eyepiece or ocular lens. So students, tell me, if the power of the objective is 40x and that of the eyepiece is 10x, then what would be the final magnification? If your answer is 400x, then you are correct. A standard microscope will provide you with a final magnification range of 40x to 1000x as can be seen here. 40x, 100x and 400x. We will talk about the 100x objective which gives 1000 times magnified image in the coming slides. The magnification beyond the resolving power is not of much importance because the image would be larger, but it would be fuzzy and its details would not be seen. This can be compared to the distance between us and a movie screen. If we sit too close to the movie screen, the image is very large, but at the same time it is blurred and less sharp, not allowing us to even recognize the faces of our favorite cine stars. Hence, magnification without resolution is considered to be useless. The next terminology is working distance. This is the distance between the objective front lens and the top of the glass slide when the specimen is in focus. In most instances, the working distance of an objective decreases as magnification increases. The working distance with a low power objective is 4 to 8 millimeter, with high power objective is 0.5 to 0.7 millimeter, and with the oil immersion objective is 0.1 millimeter. What is critically important here is the angle. Remember the angular aperture A? Half of it is theta. Do you remember the formula for numerical aperture? Yes, it is Na is equal to n sin theta. So, greater the value of theta, greater will be the value of Na. For a low power 4x system, the numerical aperture is going to be very low, around 0.12. In a medium power 40x system, it could be in the range of 0.34, and for a high power system, it can be as high as 0.87. Also, do you remember the relationship between Na and Rp? From the formula, greater the numerical aperture, greater is the resolving power. Let us now talk about the oil immersion objectives, also called 100x objectives. Continuing from the previous slide, from the equation, we know that greater the Na, greater is the resolving power, and Na is equal to n sin theta. The refractive index n of air is 1. Theoretically, the maximum value of theta can be 90. This means that sin theta cannot be greater than 1 because sin 90 is equal to 1. Therefore, no lens working in air can have an Na greater than 1. We know that greater the Na, more is the resolution. So obviously, to increase resolution, the Na has to be increased. And the only practical way of increasing the Na is to use a medium with a higher refractive index, thus increasing the value of N. Generally, immersion oils like cedar wood oil or paraffin oil are used for this purpose, which have a refractive index of 1.52. Oils have an advantage of not evaporating when exposed to air for a long time. Also, oils have the same refractive index as that of glass. We will see the importance of this particular point. The fact that oils and glass have same refractive index reduces the loss of light rays entering the front lens of oil immersion objective by refraction, as you can see in the picture. When air is the medium, some light rays are lost as a result of refraction. See the pink light ray which is not being collected by the objective lens and which is moving out of the path. The immersion oil provides a homogeneous path for light to travel between slide and front lens of the objective. See the blue ray here. It has a homogeneous path as it is passing through the glass slide and the droplet of the immersion oil. And as a result of that, it is collected by the objective lens. Also, while working with oil immersion objectives, the working distance is very small. As a result, the angle theta increases as was shown in the previous slide, along with an increase in the numerical aperture from 0.12 to 0.87. Thus, oil immersion objectives serve a few important functions. They increase the numerical aperture by increasing the refractive index N of the medium. The refractive index of air is 1 and that of immersion oils is 1.52. Further, oil immersion objectives increase the numerical aperture by increasing the value of sin theta. Remember, numerical aperture is equal to n sin theta. The oil immersion objectives prevent loss of rays by refraction. Hence, they allow maximum rays to enter the objective lens and thus achieve a magnification of 1000x.